Welcome back to part B of the Putnam 2021. We got 3 really interesting problems to cover today, and I promise you that you will absolutely love the solutions. Without further ado, let us take a look at the first problem, which is actually a probability problem. So problem B1 is as follows. Suppose that the plane is tiled with an infinite checkerboard of unit squares. If another unit square is dropped on the plane at random, with position and orientation independent of the checkerboard tiling, what is the probability that it does not cover any of the corners of the squares of the checkerboard? So this is the type of question where you read and realize that it's a very natural sounding question, but you wonder why have you not thought of this question before in your life. So indeed, this is quite a feast. So let's take a look at what the solution is. Now, for a start, we will fix the angle theta with respect to which the drop square is oriented. Later on, we will sum over the angle theta with an integral. So we fix theta first. And now suppose we know the center lies in a particular grid unit square. The question we should ask is, where can the center be within the grid unit square? The area of the allowed positions for the center will give the probability for this particular orientation of the pink square. Actually, it turns out that maybe it's easier to ask where the square cannot be. So for example, the center cannot be here because it will cover this corner. So the question becomes, where can the center not be within the grid unit square? Let's tackle a slightly easier question first. What spots of the center will cause the red square to cover, in particular, the bottom left corner? Well, to answer this, we'll put a copy of the unit square oriented at our fixed orientation, centered at the bottom left corner. Then I claim that if the red center lies in this yellow square, then it will cover the bottom left corner. So this is actually by symmetric relationship between the yellow and red square. So in other words, the yellow square gives the forbidden region for the red square because it will cover the bottom left corner. We can do this for each of the corners by putting a copy of the unit square at the fixed orientation at each of the corners. And this gives in total the forbidden areas for the red center. So in other words, the tiny white square left in the middle is actually where the center can be. So we need to find the side length of this tiny square. Okay, let us simplify this diagram a bit to the bare essentials. We need to find the length of the tiny square, which is actually the parallel distance between two lines. This line is actually the bottom of this square that was centered at this corner. So it lies at a distance half away from that corner, incline at an angle theta here, and this gives the bottom edge of that square. And then the other line is the top edge of the square that is centered at this corner. So it's located at a distance half away from that corner where the blue arrow is inclined at angle theta. And this gives the top edge of that particular square. So we need to find the distance between these two brown lines. There are many ways to do this, but one direct way is to use coordinate geometry. So I'm just going to let this be 0, 0, 1, 0, 0, 1. Now, this is length half and theta here. So this part is 1 over 2 cosine theta. Is the hypotenuse of the right angle triangle, right? So I know the coordinate of this where my cursor is now, which is basically x coordinate is 1. The y coordinate is 1 over 2 cosine theta. So I know the coordinate and I know the slope of this line is actually tangent theta because it's inclined at angle theta. So I can write down the equation of this line. I know the point and the slope, so this is the equation. So this means I can find the y-intercept, which is actually the y value here by just putting in x equals 0 into the equation. So I get the y-coordinate of the intercept is given as follows. And I also know the y-coordinate of this other line because it's just 1 minus this distance, which is 1 over 2 cosine theta as well. So this is the y-coordinate. So if I take the difference of the two y-coordinates, I'll get the vertical distance is actually 1 minus 1 over cosine theta plus tangent theta. And the slanted distance, which is the blue distance that we want, is the cosine of that. So the blue distance is cosine theta minus 1 plus sine theta. And now the area of the eligible white square is actually the square of the blue arrow. So the probability of being good is cosine theta plus sine theta minus 1 quantity squared. Okay, so this is for the fixed angle theta, but in the end it's quite straightforward. We just integrate over all theta. So this is for fixed theta, this is the probability of being good. We integrate from 0 to pi over 4, because after that, by symmetry, you can go back to one of the earlier cases in 0 to pi over 4. We divide by pi over 4, so that's why there's a 4 over pi here. And to do this integral, we simply just expand the square, and this is a really basic calculus question. So I won't go through the computation, and you should get 2 minus 6 over pi. So I must say this is quite a difficult problem for B1. It's definitely harder than usual, but nonetheless an interesting problem. We have two more pretty exciting problems coming up. The next one is an algebra problem. So for this problem, we are supposed to determine the maximum value of this sum. Sum from n equals 1 to infinity, n over 2 to the power n, a1, a2, an, this whole thing to the power 1 over n. And this is over all sequences a1, a2, of non-negative real numbers, satisfying sum of all the a's equals to 1. So when you see this quantity over here, it's screaming to you to use AMGM. So what is something we will naively try it first? The naive way of applying AMGM is just to use the standard form. This is the GM, is less than or equal to AM. And you might think, yeah, it looks rather promising, because if you put it back into the sum, the ends will actually cancel each other out, and it looks like something reasonable is going to come out of it. But actually, you can quite quickly realize that this is not going to give you a tight upper bound. Why? This is because if this were to be equality, you will need A1 equals A2 equals A3 and so on. And you need equality term by term if you want this to be a tight upper bound, which means you will need all the a's to be equal, but you cannot have all the a's being equal to each other and still have this sum being fulfilled. So this looks like it's not a very wise way to use AMGM. Now, intuitively, what will you try to do? You see that you will want the a's to decay to 0, which means you will want the AMGM to be weighted with the weights here increasing from A1 to A2 to A3 to AN, so that when equality holds, the a's will be decaying. So this gives you the idea to instead, let's write the product with weights attached to it. So I attach weight 2, 2 cubed, 2, 5, and so on, and then I divide by the weight, product weight, so that the two sides of the equal sign are equal. And you might ask, why did I choose the weights 2, 2 cubed, 2, 5? It seems pretty random. Well, actually, I chose it this way so that you know the sum of odd numbers gives n square. And so when you take 1 over n, the 2 to the n square becomes 2 to the n. So this is why I chose this particular formulation. It gives a very nice coefficient in the bottom that can be taken 1 over n. So 1 over n, 1 over n, and then this is just 2 to the n, which will combine very nicely with this. So let's see this in action. We write the product as follows. So when we use the AMGM applies to this top part. This is the GM. So we put it in weighted form. This is the AM in weighted form. And so let me tidy up the terms a little bit. Now I put in the n over 2 to the n together with the product. So the full term by term, this is the summand, and the n's cancel. The 2 to the n combined to 4 to the n. I pull out a factor of 2 common to the top to write 2 here, and then the sum increases by a factor of 4 each time. So very nice, you have 4s appearing in places. That seems to point to something promising. So we can now try and finish the problem. Let us take a finite sum so that we will not run into crazy limit problems. Let's take a finite sum up to capital N. Term by term, we can apply the formula from the previous slide. We get this expression here. And now we can try and rearrange the sum along the a's. So collect all the A1 terms first. Well, A1 appears in n equals 1 all the way to capital N. So you have A1 and then the coefficients from n equals 1 to capital N. A2, it appears, for A2 rather, for A2 appears when n equals 2 to capital N. That's why you have here the coefficients running from 2 to capital N, and so on. The last term will actually be A capital N. That appears only when n equals capital N, so you have this coefficient here. But the very nice thing is that actually we can bound each of these by the infinite sum version. So this sum from 1 to capital N is less than or equal to sum from 1 to infinity, right? And the sum from 1 to infinity of this is 1/3. At the same time, this one, if I put a copy of 4 inside the sum, now this runs from 1 to capital N minus 1. That is also bounded by the sum running from 1 to infinity. So same thing, 1/3 appears here. This one I can put into the summand. Now it runs from n equals 1 to 1, again bounded by the sum it were to run from 1 to infinity. So that sum to infinity is also again 1/3. So you have this inequality here, and you can take out the 2/3. You have a1 dot 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 to a capital N, and of course this sum is less than or equal to the sum to infinity of the a's, which is 1. So this whole thing is less than or equal to 2/3. So now I have a bound that is less than or equal to 2/3, and even though we took the finite sum here, right, we actually have a bound that is tight. Now, to show that it's tight, we basically need to come up with a construction to show that we can get s equals to 2/3. And it's actually pretty straightforward to do it, because by the AMGM, you will want equality to hold all the time. So you will want A1 to be 4 times of A2, 4 times of A3, 4 times of A4, and so on, such that the sum equals to 1. So you can very easily solve that to come out that AK equals 3 over 4K will satisfy this sum. But you can also now substitute this into expression for S and work through the computation, and you will get 2/3 as the result. So that's really all there is to problem B2. It's a very nice problem that uses AMGM in a creative manner. And I think this is something that IMO contestants should be able to tackle. And lastly, we have a number theory problem. And I promise you, this is really one of a kind. This is something that is so beautiful. Now, for this problem, it's actually problem B4. I skipped B3 because B3 is actually a analysis problem, real analysis problem. So I thought B4 being a number theory problem would be much more interesting to cover. So here we have F0, F1, etc. is the sequence of Fibonacci numbers. F0 equals 0, F1 equals 1, and so on. Now for m larger than 2, we let Rm be the remainder when this weird looking product is divided by Fm. Prove that Rm is also a Fibonacci number. Okay, I'll try and digest what the question is first by going through a few small examples. So here we have the table of M, and this is the Fibonacci sequence. What happens for the first case we need to consider M equals 3. Okay, so M equals 3, what is this product? This product, basically it runs Fm here, when m is 3 is 2, right? So it runs from 1 to 1. So basically this product is just 1 to the power 1. We are looking at mod of Fm, which is 2 in this case. So this thing is congruent to 1 mod 2. 1 is indeed a Fibonacci number, so okay. It's more interesting when you look at m equals 4 and m equals 5. So for m equals 4, the Fibonacci number is 3. So the product runs from 1 to 2. So we have 1 to the power 1 times 2 to the power 2. And we are taking mod 3. So this thing is actually 1 mod 3. So, okay, again, 1 is a Fibonacci number. Now, m equals 5 will give you the pattern of what's going on already. So, the product, now Fm is 5. So, product runs from 1 to 4. So, you have this product here. You are taking mod 5. You can work out that this is actually congruent to 3 mod 5. So, 3, again, is a Fibonacci number. So, very good. So, having worked through the small examples and get a comfort of the nasty looking product, now let us prove the problem for m bigger than 5. Now, after a bit of experimentation, you will very quickly realize that if Fm is a composite, then actually this is very straightforward. Because if, let's say, Fm is written as A times B, where A and B are smaller than Fm itself, A and B will appear in this product. So obviously this thing will include A times B, so this will be congruent to 0 mod Fm. So for composites, we are done. We only need to focus on Fm being a prime. Now, at this juncture, I will take a short pause to cover a famous lemma. This lemma is actually the key to this entire question. So this lemma is actually the Cassini's identity, which says that Fn plus 1, Fn minus 1 minus Fn squared equals minus 1 to the power n. So if you have not seen this identity before, you might worry that you might not be able to solve the problem, but actually you will be led quite naturally to something that you need to prove as you work through a problem. But this lemma is just the most natural way to prove the statement that we want at the end of this slide. Now, if you find yourself wanting to prove something like this, you can obviously try and use induction. So induction will give you a very easy solution, but I want to take the opportunity to show a really nice way to prove this. The nice way to prove this is to use matrix. So you can actually write this identity, this expression, as the determinant of this matrix, because this times this minus this times this gives you basically this. And then you can actually also use the well-known fact that this thing is given by the nth power of this matrix. Well, you can use induction and very quickly see that this is true. So this is actually a very nice fact about Fibonacci numbers. You can generate by taking powers of this matrix. And now determinant of this power is the power of the determinant. And this is just minus 1 to the power of n. So a very neat proof of the Cassini's identity. Now what we actually really want from this lemma is the fact that Fn plus 1 therefore divides Fn squared plus this thing minus 1 to the power n. So I wrote this here, and I'm going to shift the index down by 1 because that is really the form we'll be using. So Fn divides Fn minus 1 squared plus minus 1 to the power n minus 1. Now, and what we really want is the fact that we write this in mod form. So Fn minus 1 squared is congruent to minus 1 to the power n mod Fn. Yeah, so this is what you will need to prove when you try and work through the problem from the first time. Then you will realize that, okay, to prove this, maybe one of the things you try and do is, there are different ways of doing it, but Cassini's identity is really the most straightforward way. Okay, so let's park this in the back of our mind and return to the problem. So recall that we are trying to prove that Fm is a prime, prove the solution when Fm is a prime. Now, the funny thing is that when Fm is a prime, this is another nice fact about Fibonacci numbers. Actually, when Fm is prime, m cannot be even. So why is that so? If m is even, now we recall our corollary. Fm minus 1 squared is congruent to minus 1 to the power m, congruent to 1 because m is even, mod Fm. Now, Fm is prime. That's what we assume. Fm is prime. So we have a few over here. This implies that Fm, the quadratic equation, x squared congruent to 1, right, only has the two solutions plus minus 1. So Fm minus 1 must be congruent to plus minus 1. This again because we are working over a few. So polynomials like x squared minus 1 will have two unique solutions, up to two solutions. And we know the solutions are plus minus 1. So this must be the case here now. So this means Fm minus 1 is either equal to 1 or Fm minus 1 because, I mean, Fm minus 1 is smaller than Fm itself, right? So the congruence means it's either 1 or directly Fm minus 1. And you can check that this cannot be the case for m bigger than 5. There's no way the Fibonacci number is either 1 or just 1 smaller than the next one. So this is a contradiction, and we know that m must therefore be an odd number. Now, what's more is that once we know m is an odd number, we can see what's the behavior of the prime mod 4. Here is the table of Fm when taken to modulo 4. So this is just the Fibonacci. You can just very quickly write down the sequence, and then you realize that the pattern repeats itself in cycles of 6. So if you look at m being an odd number, and we want Fm being a prime, we see that the only possibility is actually Fm congruent to 1 mod 4. It cannot be congruent to 3 mod 4 at all. So what we really know now is that if Fm is prime, firstly m is odd and Fm is congruent to 1 mod 4. And of course, I'm going to just write my Cassini identity corollary here because we'll need to use it yet again later on. Now here comes the killing blow of the question. This is your strange looking product. Now a very natural thing to do is write that out as many copies of 1 to fm minus 1. So you have 1 copy of 1, 2 copies of 2, 3 copies of 3, and so on, fm minus 1 copies of fm minus 1. Now when you write it in this form, well, the first row looks like fm minus 1 factorial, right? And that's very nice because by Wilson's theorem, you have that congruent to minus 1 mod fm. Okay, but how about the rest? Well, you realize that you can pair this last row with the second row by moving this thing here and flip the sign. So this thing is actually minus 1, mod minus congruent minus 1. So you can put it 1 and put a minus sign in front. You get minus of the whole factorial. So this is actually congruent 1 mod fm. So you can pair the second last row with the third row. Again, you get some copy of 1 or minus 1. You can do such pairing and keep getting copies of 1 and minus 1, except the very row in the middle where you have exactly half of the terms on the right side. So you have half of the term on the right side and you are lacking the left side. But you realize that because fm is congruent 1 mod 4, right? So half of these terms here is an even number of terms. So if I flip all those terms to the front half instead, I'll get fm minus 1 over 2 factorial, and I incur an even number of copies of minus 1 because I flip an even number of terms over to the front half. So I get this is not minus 1 but plus 1 times the left half factorial. So fm minus 1 over 2 factorial. Okay, so I have a whole bunch of 1 and minus 1s, which I can tell you later on that we don't need to care about them. And then this is fm minus 1 over 2 factorial. We need to simplify this. Now comes another number theory fact. So we note that actually the square of this, right? What is the square of this? The left half and the right half are both congruent to the same factorial. So if you take this factorial square, is actually the entire factorial itself. So it's all equal to fm minus 1 whole thing factorial. And this thing again by Wilson's theorem is congruent to minus 1. So we need to find the roots of this x squared congruent to minus 1 solution. And here is where the Cassini corollary comes in. You know that fm minus 1 squared is congruent to minus 1. So fm minus 1 and minus fm minus 1 are the roots of this equation. So the factorial itself is either congruent to plus or minus fm minus 1. So this is absolutely crazy because you have a whole bunch of 1s or minus 1, and then this last gigantic term here is plus or minus fm minus 1. So everything together is basically products to plus or minus fm minus 1. And why is this a Fibonacci number? Well, I mean, if it's plus fm minus 1, I mean, it's obviously a Fibonacci number. But even more so, when it's minus fm minus 1, you realize that you're taking mod fm. So that is what? Fm minus 2. So this is by the recurrence relation of the Fibonacci number. So you either have fm minus 1 or fm minus 2, and that is the end of this problem. So a very, very nice problem that uses a lot of number theory facts and interesting properties of the Fibonacci numbers. So I hope you learned something from this problem. And next week, we'll probably be covering the China Math Olympiad because I understand that it will be out around this week. So stay tuned and see you soon.